the quiz last time, right? I don't have it. I don't have it graded yet, but I'll have them back on Monday. And there's no lab this week, but if you have any questions about homework or anything like that, if you want to come talk to me about it after class, I'll be in there for a while. And the first exam is starting to be on the horizon. I think it's 2 weeks from, it's like 12 days from now, like 2 weeks from Monday. I think so. Yeah, September 18th. So I guess next Tuesday, I'll tell you what topics are going to be on it. I think it's probably going to be problems related to the unit conversions problems and problems related to 1D kinematics. And so I think today we'll finish everything we need to do, all the 1D kinematics problems, and then we'll spend the next couple of classes just doing example problems, and I'll give you problems to work on together and that kind of stuff. Anybody have any questions before I start with new stuff? Yes. Well, it just depends so much on what kind of problems, you know. But my goal in writing the test is always to write a 1 hour test, and then you have an hour 25 or whatever to do it, you know. So I think you'll find that you feel like you have enough time to do it, you know. I always I always feel like I wrote the right length test, the test length that I meant to, if half the class is gone after an hour, you know, and then half the class stays into the last 25 minutes. So I try to give you plenty of time to space out and think about a problem and go back and come back and that kind of stuff. But some problem types are just way shorter than others, you know. So actually this test will be the one with the most problems on the whole test because those unit conversion problems go really fast, you know. But still there's only going to be probably 8 problems or something on the whole thing. Give me that phone. Well, we know what your ringtone sounds like, so we know. Okay. Any other questions? I like when the ringtone is like music and like music just starts playing. Makes me feel like I'm in a movie, like I'm like a movie about a college or something. Like I'm about to make some important, like notice something important or something. You know what I mean? No. Okay. All right. So we've talked about position and displacement, and we've talked about velocity. Last time was velocity. And remember, velocity was based on this equation that came from the average velocity. So remember, the average velocity equation was the position at the later time minus the position at the earlier time divided by the elapsed time. And I'm just writing that up there because when we talk about acceleration, it's going to look very similar to that. So the last thing we have to talk about is acceleration. That's the last kinematic quantity before we can start doing problems. And just as velocity tells you how quickly position is changing, Acceleration tells you how quickly velocity is changing. And based on that, you might expect that the similar for the equation for acceleration would look similar to this, except instead of positions in the numerator, it would have velocities, and that's exactly what it is. So the acceleration is equal to, let me elaborate on this a little. So choose two instants, time 1 and time 2. Then the acceleration is the velocity at time 2 minus the velocity at time 1 divided by the difference in times. That's a really important question. So that's the first thing that's the next thing that I'm about to say. So as far as accelerations, there are a bunch of things to keep in mind. So notice, and I'm just going to list these things out. Yeah. And the first one is, for us, in our kinematics calculations, there's no distinction between average acceleration and instantaneous acceleration. There is, there really can be a difference between those, but just because of the kinds of problems we're going to do, we don't have to worry about that. So for us, there's no distinction between average and instantaneous acceleration. And that's because we'll be doing problems where the acceleration is constant. And so if the acceleration never changes, then the average acceleration is the same as the instantaneous acceleration at any instant. So we don't have to worry about that. Remember, with velocity, I defined average velocity, and then I described this sort of pinching idea where you chose those 2 points closer and closer and closer together, and the average velocity approached this thing called the instantaneous velocity. We don't have to worry about that for acceleration. The second thing is, in 1D, a non-zero acceleration can only mean two things. It means an object is slowing down or speeding up. And that is because in 1D, there are only two directions, positive and negative. And so changing velocity, the only options available are those two things, speeding up and slowing down. They correspond to the two directions. When we go to 2 dimensions, you can have velocity in infinitely many directions, because velocity, the direction of velocity is the direction of things going. It can go, anywhere in a plane. And so when we get to 2 dimensions, velocity can change without the speed changing. So anytime an object is turning, it has acceleration. Okay, but there's no such thing as turning in 1D. And so in 1D, where we're starting, it's just speeding up or slowing down. And then third, how you determine whether something's speeding up or slowing down based on the acceleration is not what you would probably guess. And I think what most people would guess is, since in our everyday language we talk about acceleration as opposed to deceleration, so I think it's because we break it up into those two things that people tend to think like positive acceleration is probably going to be acceleration and negative acceleration is probably going to be deceleration. But that's not how it works. It's a little more complicated than that. So here's how the signs of acceleration relate to speeding up or slowing down. First of all, if the velocity is equal to 0, then the object's at rest, and so any acceleration means it's speeding up, right? You can't slow down from 0. So if the velocity is 0, any acceleration makes it speed up. But now, here's where, it behaves in a way you probably wouldn't expect. If the velocity and acceleration have the same sign, then the object is speeding up. On the other hand, if the velocity and acceleration have opposite signs, then it's slowing down. And so if an object, another way of thinking about it is, if you have an object that's moving this direction, so say that's the direction of motion, what would be the direction of acceleration if the object is speeding up? Yeah, has to be in the same direction, okay? Whether that's, so what direction is that? Is that positive or negative? Yeah, we don't know yet because we haven't decided. That's one of the things you have to decide before you put numbers to things. But if we chose that as our positive direction, the acceleration would have to be positive. And if we chose it as that is the positive direction, our velocity would be negative and our acceleration would have to be negative. So if it's speeding up, they're both in the same direction. If it's slowing down, they're in opposite directions. Question? Oh, no. So if it's speeding up, the acceleration direction is this way. If it's slowing down, the acceleration direction is this way. Now here's something that's going to be confusing, kind of on and off throughout all the kinematics. It'll be confusing, and then it'll make sense, and then it'll be confusing again. You know, it sort of keeps messing with your head as you're learning this stuff. But what I want to do is just show, using this way of thinking about things speeding up and slowing down, that an object that's in free fall, an object that where the only thing acting on it is gravity. So an object acted upon only by gravity has downward acceleration no matter which direction it's moving. Okay, so imagine an object that you throw straight up into the air. Okay, so first of all, think of an object on the way up. So that's the direction of motion. When you throw an object up into the air, is it speeding up or slowing down? It's speeding up when your hand's on it, but as soon as you let go of it, it's slowing down. You know it has to slow down eventually because it doesn't keep going forever. Eventually it stops and turns around. And so since it's slowing down, the acceleration has to be this way, right? This is the direction of the velocity, is up. Okay, so an object on the way up has to have, I mean, in the special case where the only thing acting on the object is gravity, an object that's on the way up has to have a downward acceleration. And now let's think about an object on the way down. So the direction of motion is down, and that means the velocity is down. Is that speeding up or slowing down? Speeding up. And so which direction is the acceleration? Yeah, the acceleration is still down. And in fact, it always has the same value. The acceleration of gravity in free fall is 9.81 meters per second squared down. Any questions about that? Okay, so usually we will use negative, but again, we can't put signs to that until we've chosen a positive direction. So we are going to, I'm going to recommend that you always choose up to be positive, and then, yeah, that acceleration will always be negative. But you can think of it as the acceleration of gravity doesn't have a sign on its own. All it has is a direction, and you choose whether that direction corresponds to positive or negative. You know. Okay, so now we've talked about, defined position and velocity and acceleration. And all of the equations we've used are, they were just to introduce those topics, to define those quantities. But now I'm going to introduce the three equations that really are the only three equations we're going to use for all the problems in this section. So these are the equations for this section. Equations for what these represent is one-dimensional kinematics constant acceleration. So these three equations don't apply if the acceleration is changing. But as long as the acceleration stays the same all the time, then these apply. And free fall is going to be the most important case of that. So if you define these variables pi and vi as the position and velocity at time 0, and bless you, and pf and vf as the position and velocity at time t final. The f is for final. Then here are the three equations we're going to use. First, velocity final is equal to velocity initial plus a t final. Second, position final is equal to position initial plus velocity initial times t final plus 1/2 a t final squared. And then the third one is 2a times the quantity p final minus p initial is equal to v final squared minus v initial squared.
These things that we should be committing to memory?
No, I'll give you these on all the tests. You just have to know how to use them. And now I'm just going to give you a list of 4 steps for using these, and then after that we're going to spend a bunch of time just going through example problems. Any questions yet? I don't know. You should not have any questions yet. Here's a hint. No, you don't. Yeah. Is that a question? Yes. Yes. Yeah. So with the right, it's just in either case it means the position or velocity at time. In either case, it's the position and velocity when time is equal to 0. So here are the steps for using the constant acceleration equations. So first you have to make these 4 choices. You have to choose an instant corresponding to time equals 0. You have to choose an instant corresponding to time final. You have to choose a location corresponding to position equals 0. and you have to choose a positive direction. The first pair and the second pair are kind of fundamentally different. Choosing the instance corresponding to those times, most of the time there's no there's kind of a right and a wrong to that. Sometimes there's more than one right choice, but if you choose these wrong, you can't do the problem. These are different. These are totally arbitrary, and you choose these just to make sure that you're consistent throughout doing the problem. So these two are arbitrary. Choose them however you want, and you can still do the problem. But these two, you need to make those choices based on when you have information about the motion and when you want to find information about the motion. T final always has to be later than time equals 0 because we are never going to use negative times. So those are just two instances where you're given stuff or you're asked for stuff. The second step is list out the variables you know values for. And the variables you want. Well, there are only 6 variables that we're dealing with in these problems if you look through all of these. There's time final, P initial, P final, V initial, V final, and then the acceleration. So you can just go through that list of 6 variables one by one and think, like, am I given, do I know from what they've given us a value for that, or am I asked for that? And I think that's like a fire drill. Yeah. All right, so list the variables you know and the variables you want. And the complete list is time final, position initial, position final, velocity initial, velocity final, and acceleration. So I'm going to just, every time when we do example problems that I list out what we know and what we want, I'm going to try to just think about it in that order. Do we know this? Do we know this? And then the last step is, out of those 3 equations that I gave you, look for an equation where every variable is known except the one that you're trying to find. The one you want. And that's because a single equation you can always just use to find one variable. So the variable you're trying to find, the one you want, has to be in it, and it has to be the only unknown variable in the equation. Sometimes there'll be a extra step. you'll see that when, like in the harder problems, you'll look through the equations and there aren't any that meet these requirements. So sometimes there isn't an equation that works. When that happens, you need to find an intermediate variable. And that's almost always going to be either time final or the acceleration. And then once you've found that, go back to step 2. Because now, say your intermediate variable was time final. Now you also know time final, so you can put that in the column of things that you know, and then try to find an equation that works. Anybody have any questions before? I mean, I don't think any of this probably makes too much sense before we do any example problems, but I think it'll, hopefully start to iron out issues as we go through examples. So the first example problem, let's say there's a car traveling at 30 meters per second. And when it's at that speed, it hits the brakes. And let's say that it takes 20 meters to stop. What's the acceleration? And what's the elapsed time? How much time does it take for it to stop? Okay, so this car is driving this way. You can tell it's going to your right because of the way I slanted the wheels like that. Makes it look like it's going fast. I learned that from Dr. Seuss. Yeah, that's true. Okay, so it hits the brakes here and continues for 20 meters. And once it gets here, it's completely stopped. So the first thing we have to do is make those 4 choices. The 2 that are important, most important, are those 2 time choices. And then the 2 that we can choose anything as long as we're consistent throughout the problem are the position ones. So to make the 2 time choices, we have to choose an instant for time equals 0 and an instant for time final. And those have to be at instants where we have information and where we want information. So based on that, what's going to be our time equals 0? Yeah. Right when the car hits the brakes, we know the speed. We can turn that into a velocity. And 20 meters later, we're going to be able to figure out what the position is. And we also know the velocity is 0 because it's at rest. For the acceleration, well, the acceleration is constant, so that's going to be the same over the whole thing. So that doesn't change our minds about anything. So we want to choose time equals 0 to be when the car hits the brakes. And time final when it reaches rest. And now the two position ones. If you don't have any other reasons to do, yes?
So we're trying to figure out how large the
That's the second thing we're trying to figure out, yeah.
okay. Yeah, but we're determining how long it takes to stop that. Like we can decide how long that time. So
No. So what we did here, so we don't get to choose what these values are. We just get to choose what physical instance they correspond to. Okay, so we chose that time equals 0 is when it hits the brakes, and we chose that time final is once it stops. But we don't know yet what number this is going to be, and what we're trying to find is the number. Okay, so if you don't have any reason to choose anything different, I always just choose position equals 0 to be the object's position when time is equal to 0. So position equals 0 then is going to be right here. The location when the object starts braking. And the car hits the brakes. And then also, if there's no good reason to choose something else, I'll choose the positive direction to be the direction of motion. So this is the 0 and positive is going this way. Any other questions about those choices? Okay. So now the second step is we're going to list out the variables we know, the ones we want. I'm just going to go in order through that list of variables. Okay, so do we know the amount of time between time equals 0 and time final? No. We want to do that for part B, but I'm going to leave that off for now. We'll just do part A first and then come back. So we don't know what that is, and we don't want it. In other words, if we can solve this problem without getting that time, that's fine with us because we weren't asked for it for part A. So then the next one is the position when time is equal to 0. Okay, what's that? Yeah, we chose the 0 position specifically to be the location that the car is at when time is equal to 0. So this is equal to 0. Do we know the position at time final? Yeah. Okay, so and figuring that out is kind of the same process as those kind of problems we've done where you have the house and the shore and you choose a 0 position and a positive direction. And then you have to figure out what the positions of things are based on how far you've gone in the positive or negative direction. It's the same thing here. If we know it's 20 meters between here and here, and this is 0, then what's the position of this if you go 20 meters in the positive direction? Plus 20, yep. And then the next one is the velocity at time equals 0. Do we know what that is? Yes. Well, I'm saying it here because it could be negative 20, and that would change the answers. So I'm just trying to be clear that you need to make that decision. Okay, what about the velocity when time is equal to 0? Okay, we do know that, so I'll put it here. What we're given, though, is a speed. The speed's 30 meters per second. So the sign of the velocity we're going to have to figure out from our choice of positive direction. So is this car moving in the direction we chose as positive or negative? Positive. So that initial velocity is positive. Yeah, well, I drew this picture, and I just drew the picture of the car going, like we could be on either side looking at it. But what determines the sign of the velocity is we know that once we drew this picture, the car is moving in this direction. Okay. And then we made the choice that that's the positive direction. So that's when it became required that the velocity be positive. Okay, what about the final velocity? Yep, that's 0 because it stops. And then the last one is the acceleration. Do we know that? No, and that's what we're trying to find. I'll put that over here. Oh, well, you can, but it doesn't. If you think of a number and a unit as like a number times a variable, if you multiply 0 times anything, it's just 0. So you can write it or not write it. Okay, so step 3, we're looking for an equation that has A in it. This has to be in it, so we can solve for it. And anything else that appears in the equation is known. So of those 3 equations I gave you, do any of them meet that requirement? The last one, yeah. So the first one doesn't because we don't know time final. The second one doesn't because same thing, we don't know time final. The third one, we don't know A, but it's in there, so we can solve for it. And all the other 4 variables in the equation, we know. So the equation we're going to use is 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. Okay, so now I'm just going to fill in the variables that we know. So we have 2A times the quantity 20 meters minus 0 is equal to 0 squared minus the quantity 30 meters per second squared. And so I'm going to multiply this out. The left side becomes 40 meters times A. And the right side, you have to square everything in these parentheses. So you get 900 meters squared per second squared. And then the negative isn't in the parentheses, so that's negative. And then I'll divide both sides by 40 meters. So we get A is equal to negative 900 meters squared per second squared divided by 40 meters. And now to do that division, I'm going to write these values out the way that I write them out for unit conversions. And you'll see that, we can cancel some of the units. We'll come out with a set of units, and the units we come up with will be the ones that we should get for acceleration. So, yeah. Yes, it's going to be awesome. So acceleration is equal to negative 900. All right, this is meters times meters over seconds times seconds. And then we're dividing it by 40 meters, so we're just going to take the reciprocal of everything there. So put the 40 meters in the denominator. One of those meters cancels. And we get an acceleration that's equal to 9. Oh, yeah, that's negative 22.5. And the units are meters per second squared. And those units of meters per second squared, how does that compare to the units you should get for acceleration? You don't know because I forgot to tell you. But the units of acceleration are always length divided by time squared. And so the SI units are always meters per second squared. So it matches. Okay. Does it make sense that the acceleration is negative? Okay, yeah, so how can you figure that out? Well, this whole problem is about this car slowing down and stopping. So you know that the signs have to be what's required for slowing down. The velocity is positive, and so if it's slowing down, that means the acceleration has to be negative, and that's what we got. Negative 22.5 meters per second squared is a lot. And if you think of it in terms of numbers of g accelerations, numbers of g's, what I said up here was 1g is 9.81 meters per second squared. So 22.5 is like over 2 g's. So that's a big acceleration. Okay, the second part of this is now we're trying to figure out the amount of time. We're trying to figure out time final. Is there any reason to choose any of, change any of our choices for time equals 0, time final? So that's the first question. Time equals 0, time final, position equals 0, positive direction. Well, these first two are based on where we know stuff and where we want stuff. We still know all the stuff we did before, plus we know acceleration. So our old choices for time equals 0 and time final still work in that sense. But now we're trying to find time final. Well, that doesn't make us change what we want to choose as our instant corresponding to time final, because, I don't know, that is itself the thing we're trying to find, We'll keep these two the same. And is there any reason to choose a different location for position equals 0? No, and no reason to choose the positive direction. Remember, these two are arbitrary, so might as well keep it the same. If we keep all four of these things the same, then all the values we figured out before we can just use in the new problem. So now let's list out what we know and what we want. All the stuff we knew before we still know, so if I go through in order, the first one that comes up is time final. That's the one we're trying to find. And then we know P initial is 0. P final is 20 meters. V initial is 30 meters per second. P final is 0. And what we know now that we didn't know in part A is we know now the acceleration is negative 22.5 meters per second squared. Okay, so is there an equation out of those three that works for this? The first one, and I think the second one would too, but in that case, if you have a choice, you might as well always take the simpler one. So that first equation is always the simplest one. Take it if it's available. So we're going to use the one that says V final is equal to V initial plus A times time final. Bless you. V final is 0. V initial is 30 meters per second. A is negative 22.5 meters per second squared. T final. And so I'll subtract 30 meters per second from both sides. Negative 30 meters per second is equal to negative 22.5 meters per second squared times time final. And then divide both sides by negative 22.5 meters per second squared. I'm just going to switch stuff over to the other side. But so we have negative. Okay, so now to do this division, I'm going to write out negative 30 meters per second the same way that I would for a unit conversion problem. So we have negative 30 meters over seconds. And then I'm going to take the reciprocal of negative 22.5 meters per second squared. So that means I put negative 22.5 and the meters in the denominator, and the seconds squared, the seconds times seconds in the numerator. No, I knew to do that because that's what you do if you divide. Just everything switches its location from before. And so one of the seconds cancels, the meters cancel, and the negatives cancel. And the units we're left with are seconds, which is the right units for time final, so that's a good sign. We can also see we're going to get a positive number, so that's good because we don't deal with negative times. If you ever get a negative time, it means something went wrong. And so time final, what's 30 divided by 22.5? Ooh, I bet I could figure that out. That's what I was going to say. Yes! So time final is 1.3 seconds. Pretty good. Any questions about that? That is a better practice if you. Some people don't like that; it makes them nervous, and so I'm happy if you do it like this. But if you're comfortable doing it all algebraically first and then plugging numbers in, that's a better habit to get into. Any other questions? Yep. No. Usually, a picture like that would be included with the problem, just to, help you visualize what's happening. Any other questions? Okay, let's see. Let's do another one. So let's say there's a ramp and a ball rolls up the ramp. And at this point A, the speed of the ball is 3 meters per second. And then it reaches the highest point. So just as it's about to turn around, at that instant, it has no speed, no velocity. And so when it gets here to B, it's at rest. And between where it hits point A and where it hits point B, let's say the elapsed time is 2 seconds. And the question is, how far apart are A and B? So step one, we have to make those 4 choices. So time equals 0, time final, position equals 0, and positive direction. So what are we going to choose as our time equals 0? So the places where we know stuff, we know a velocity here, we will know a velocity here. And here, we know velocity, it's at rest, so 0 velocity. And we also, how are we going to be able to do this? Okay, so we know velocity here, and we're trying to find a position here. So when it gets here, there's stuff that we know and stuff that we want. So we're going to make this our time equals 0 when it's here, and when it's here, that's going to be our time final. Yes?
Does that ball move at the same speed until it gets to B, or does it just...
No, it's slowing down the whole time.
Okay.
Yep. So remember, all of these problems are constant acceleration. So it's always slowing down or speeding up uniformly through the whole problem. Otherwise, these equations don't apply. So we couldn't do it. So time equals 0 is when it reaches A. Time final is when it reaches B. And position equals 0. Like I said before, unless there's strong feelings about something else for some reason, might as well choose your position equals 0 to be the object's position when time is 0. So our position equals 0 is going to be A. And then I'm going to choose my positive direction up the ramp, the direction it's moving. And then step 2, we're going to list out what we know and what we want. Okay, do we know time final? In this case, we do. We were given an elapsed time of 2 seconds, so there's a time of 2 seconds between when it's at A and B. And since it's at A, and what we chose is time equals 0, that means time final is 2. Do we know the position when time is equal to 0? We do, because we chose, that's how we chose our position equals 0. We chose to call our 0 Paul's position at time equals 0. So, right. So in this case, PI is equal to 0. Do we know the position final, the position when time is TF? No, we don't know that. That's what we're trying to find. I'll put that over under want. Do we know the velocity at time equals 0? Yep, that's right. And positive or negative? Yep, our positive direction is the direction it's moving. So our initial velocity is positive, what was it, 3? And do we know the final velocity? 0. Yep, it's at rest. Okay, and then the last thing is the acceleration. Do we know that? No. Okay, so step 3. Is there any equation that works with these? Well, no, like all 3 of those equations have acceleration in them. And so you can't have PF in it that's unknown and have an unknown acceleration and still solve for something. So nothing. Nothing works. And so we have to go back, find an intermediate variable to solve for, and then hope that that can help us solve for the thing we're looking for. So step star, we're going to try to find A. Okay, so is there an equation that has A in it and everything else in it is known? Yep. So we'll use V final is equal to V initial plus A TF. So the final velocity was 0. The initial velocity was 3 meters per second. The time final, what was that, 2 seconds? So 2 seconds times A. And we're trying to find A. So 2 seconds, just switching stuff to the other side. 2 seconds times A is equal to, I'll keep that negative there, 3 meters per second. And so A is equal to 3 meters per second divided by negative 2 seconds. Any questions about that yet? And so A is equal to, I'm going to write this as 3 meters over seconds. And then I'm going to divide it by negative 2 seconds. and you get negative 1.5 meters per second squared. Okay, so does it make sense that the acceleration is negative? Yeah, the ball's slowing down as it goes up the ramp, and so the velocity and acceleration signs have to be opposite. So now we know the stuff that we did before, and we also know this. So now is there an equation that works? Yeah, the second equation. So now we can go back to step 3. We have P final is equal to P initial plus V initial times time final plus 1/2 times A times time final squared. So P final is equal to, P initial was 0. V initial was 3 meters per second. And time final is 2 seconds. And then plus 1/2 times the acceleration we just calculated, negative 1.5 meters per second squared, times time final squared, so that's 2 seconds squared. And so doing the units on this one is kind of a mess, but we can do it in pieces. So 3 meters over seconds multiplied by 2 seconds. Seconds cancel, and you get 6 meters. That's this first piece. And then that second piece, we have 1.5, sorry, first do the 1/2, so 1 over 2. And then we have negative 1.5 meters over seconds times seconds. And then multiplied by, you have to square everything in these parentheses, so that's 4 seconds times seconds. All the seconds cancel. And you get negative 3 meters. So this is coming from there. And now if we put it all back together, we get PF is equal to 6 meters minus 3 meters, so 3 meters.
If I skip a bunch of that work and kind of like know the acceleration is 1.5, you know, the deceleration, I'm sorry, 1.5, and I know that it takes 2 seconds to get from A to B, you just multiply the deceleration by the seconds. It's per second. So
yeah, but except for the first test, I want you to keep track of the units as you go.
yeah, I ended up with the right units.
Mm-hmm. Yes, that's fine. Yeah, you don't have to draw it out with those fractions like that. Yeah, that's right. Yep. Okay, does it make sense that that final position is positive? Yes, because the ball is going to end up in the positive direction from where it was at time equals 0. Any questions about that? Okay, so I posted some more problems that you can work on now. See how that goes, and we'll just keep going with example problems on Monday. Okay, no lab tonight. Yes.